Well, I had to spend some extra time. I did the what was it 5.5, and then I had to go back and in my study plan and go over it again just because it wasn't really sinking into me.
Okay,
But I think I've got a better grasp of it now. So
good. Do you need help on any of it?
no, I think it's just remembering when the problem comes up. Remembering, okay, now how do I work this particular problem?
Yeah,
How do I apply all that I should know by this point?
yeah. Going from seeing some words and symbols on a page to the actual solution really is the key to this whole section.
Yeah.
All right, well, let's go ahead and jump into chapter 9, since that's where we're at. We finished chapter 5. We're testing on it right now. And next section is chapter 9, which is also completed this week because we're only doing 3 sections from that chapter, which makes it a little easier. So let's get started. If we've got the right tool, we've got an equation that's x minus y equals 5, and another one that's 2x plus y equals 1. We recognize that these are lines. If we were to put these into slope-intercept form, solving for y, this first one would be y equals x minus 5. We would add y to both sides and subtract 5 from both sides. And this other one would be y equals negative 2x plus 1. So we've got those two lines there. If we were to graph those two, say this first one has a y-intercept of negative 5, a slope of 1, so up 1 over 1, or up 5 over 5, and we would get our line. With the second one, it has a y-intercept of 1 and a slope of negative 2, so drop 2 over 1, maybe another 2 over 1. Let me go ahead and do another 2 over 1 just to make it long enough. And we can see that this particular pair of lines intersect each other right there at the point 2, negative 3. So this whole section actually is talking about that intersection of the two lines. Section 9.1 and 9.2 are both talking about the intersection of the two lines. And we can find it graphically like we just did there, or we can find it mathematically. And mathematically, there are two different ways to solve this system of equations. A system of equations is multiple equations with the same unknowns, or at least one overlapping unknown. So the two ways we can do this are using substitution and elimination, and that's what 9.1 is all about. Finding the intersection of two lines using these two methods. So I'm going to show you both of them. And as to which one you would want to use, it kind of depends on the lines, the equations specifically, and how easy it is to use one or the other. And sometimes elimination is easier, sometimes substitution is easier. And the reality is you get used to using both. And the engineering field and in my engineering studies, I used substitution more often than elimination. But there are times like this one, when looking at these equations, I can see that elimination is going to work really well. But let's see what we're talking about here. With substitution, we solve one of the equations, and I'm going to go ahead and number these. So we solved one of the equations in terms of one of the variables. And it turns out that we actually already did that. We solved equation 1 for y. Now we know what y equals. So what I can do is I can take what y equals and substitute it in for y. And actually, I need to substitute it into the other equation for y. So I'm going to go ahead and do that. I've now got 2x plus y, which equals x minus 5, and that equals 1. So we solved equation 1 for y and then substituted that in for y in the second one. And now you can see I only have one variable. So I can add these together. 2x plus x is 3x. Minus 5 is 1. Add 5 to both sides. And I get 3x equals 6. Divide both sides by 3. X equals 2. Once I know what x equals, I can plug that in to any of these equations. It's easiest right there, I think, because we're solving for y at this point. We know that x is 2. So y equals 2 minus 5, which is negative 3. So the point of intersection, based on the substitution method, is 2, negative 3. That's the same thing we got over here when we were solving it graphically. Now let's take a look at the elimination method. I'm going to rewrite the two equations. I don't need that line. With elimination, what you do is you multiply one or both of the equations by some number so that when you add them together, one of the variables is eliminated. Now, as it turns out, I can already do that. I've got a negative y and I've got a positive y. So if I add those together, y will be eliminated. So that's what I don't need to multiply them by anything. I can just add the two together. So I get x plus 2x is 3x. Negative y plus y is 0. And 5 plus 1 is 6. Divide both sides by 3, and x equals 2. And now I can plug that into either of the first two equations. Let's go ahead and plug it into the second one, just because we can. 2 times 2 plus y equals 1. Now subtracting 4 from both sides. And I get y equals negative 3. Again, the point 2, negative 3 is the point of intersection. That is the gist of section 9.1. We've got two equations. We need to solve the system, meaning we need to find where those two lines intersect, and we can use either substitution or elimination to make it happen. Now, we will have some more complex problems, so just know that. And I'll work through several of those now. As a matter of fact, we've got some word problems even that we'll need to look at. And so I'll pull up one of those and we'll practice one of those so that you can see how that works. But those are the two methods, substitution and elimination. Do you have any questions on those at all? Okay. So let me actually do something here. That's not quite what I want to do, but we'll make this work. So we've got multiple ways that these lines can appear. I'm going to just put some line segments up here, and we'll talk about those. Let's do them down here so I can write below. Okay, we've got blue line or red lines just like that, and we've got a couple of blue lines. They may be intersecting like that. They may be parallel. I'm going to have to write that down because I surely can't draw parallel lines. Or they may be, oh, and this is going to be even worse, coincident, one right on top of the other. Now, we've got some terms that describe these. One answers the question, is there a solution? If yes, we call it consistent. So this one is consistent because there's a solution right there. This one is consistent because it has an infinite number of solutions. Those are two lines right on top of the other. There is no solution here. So actually, let me circle that because the whole thing is the solution. This one is inconsistent. There is no solution. The other question that's answered is, can you get one equation by modifying the other? Meaning, we have two lines that are identical, and I'm just multiplying by a factor. If so, we call it dependent. When the two lines are clearly not the same line, those are independent. So that one's independent, this one is independent. This one, however, is dependent. One line depends on the other, or you can get one line just by one line's equation just by slightly modifying the other. Say multiply it by 2, divide by a half. Those are the same thing, by the way, or anything like that. But you need to know these terms because it'll come up in the homework. You will be asked, is this consistent or inconsistent? Is it dependent or independent? If there is a solution, it's consistent. If there is no solution, it's inconsistent. If you can get one equation by modifying the other, it's dependent. If not, they're independent of one another. And so we need to know those terms so that we can answer those questions. But let's go ahead and pull up another equation or system of equations and solve it. I'm not going to do it graphically again, so I won't need that right now. But let's see what we've got. Say x minus y equals 5. The same one I just did. Y equals, yeah, I already did that one. So let me find a better one. 2x plus y equals 2, and x minus y equals 7. So looking at this pair of equations, again, clearly lines, because both x and y are raised to the first power. I see I've got positive y in the first equation, negative y in the second, so I can clearly just add these together, and I will get y's eliminated. So I can use the elimination method very quickly with this one. So I'm going to go ahead and add these together. 2x plus x is 3x. Y plus negative y is 0. 2 plus 7 is 9. Divide both sides by 3. I'm dividing by 3 so that my coefficient is 1. And now I plug that into, say, x into 2. And now I've got 3 where x was, minus y equals 7. Subtract 3 from both sides. Divide by negative 1. And now I've got the point of intersection is 3, negative 4. So elimination worked pretty well. I'm going to go ahead and try some substitution. Let's solve 2 for x. So I'll add y to both sides. And sub into 1. So now I've got 2 times x, which is y plus 7, plus y equals 2. Distribute that 2 through, and I get 2y plus 14 plus y equals 2. Add the y terms and move the 14 over, and I get 3y equals negative 12. Divide by 3, y equals negative 4. And now I can take that and substitute it into y right there. And I get x equals negative 4 plus 7, so x equals 3. Once again, I get the same point. X is 3, y is negative 4. So that is the solution to this system of equations, the point of intersection. And they will tell you, use the substitution method or the elimination method. And the reality is, my math lab doesn't know whether you use substitution or elimination. So you can use the one that you're most comfortable with. I do highly recommend that you get used to both methods, because sometimes one method is way easier than the other. And so it's worth it to know both and be comfortable with both methods, so that should the situation arise where substitution is best, you can just sit down and do that. And if elimination is best, you can quickly do that one. That would be a good idea. All right. Let me do another one here. X minus 3y equals 1, negative 2x plus 6y equals 5. Let's see, I'll go ahead and number these. And I think if I multiply 1 by 2, 1 times 2, so I multiply everything in equation 1 by 2, now I have 2x minus 6y equals 2. So now when I add these together, the x's will be eliminated. Negative 2x plus 2x is 0. 6y minus 6y is 0. 5 plus 2 is 7. And 0 does not equal 7. So there is no solution. Oops. And we could put these into slope-intercept form if we want to show that they're parallel. But if during elimination you eliminate both variables and end up with a false statement, then they're parallel lines. Recall that, and this is going back a bit, we have ax plus by equals c as our line. Then the slope is negative a over b, and the y-intercept is c over b. Remember, we talked about that quite some time ago. But if we now look at that, say we look at equation 1 and equation 2, the slope, negative a over b, would be negative 1 over negative 3, which is 1/3 for equation 1. For equation 2, we've got negative 2 over 6. Negative negative is a positive, and 2/6 is 1/3. So we've got the same slope. The question is, are they identical lines or parallel lines? And that would be the y-intercept that gives us that. C over b for equation 1, c is 1, b is negative 3, so negative 1/3 is the y-intercept of equation 1. For equation 2, c is 5, b is 6, so we've got a different y-intercept, so that helps show that these are indeed parallel lines. So elimination showed us that, but now double checking by looking at the slope and y-intercept of each equation, we can see that they've got the same slope, but different y-intercepts, so they have to be parallel. So that's a good thing to check. Now, I'm sure you can guess what the next one will look like, but let's show it. 2x plus 3y equals 6, and 4x plus 6y equals 12. So we've got equation 1 and equation 2. It looks like if I multiply equation 1 times negative 2, then the x's will be eliminated. So negative 2 times 2x is negative 4x. Negative 2 times 3y is negative 6y. And negative 2 times 6 is negative 12. So when we add these together, 4x plus negative 4x is 0. 6y plus negative 6y is 0. 12 plus negative 12 is 0. And it is true that 0 equals 0. So that is true, which makes this a consistent system. And if we actually, when we multiply 1 by 2, it gives us equation 2, which tells me that this is a dependent system. And so the solution is x, and what would be the y? Well, let's solve one of these for y. Subtract 2x from both sides. Divide by 3. And we would get that same equation for the other one. So for any x we pick, the corresponding y would be negative 2/3 x plus 2. That's how you write the solution to consistent dependent systems, meaning it's one line right on top of the other. You just have x be whatever you pick, and then y becomes the equation you get when you solve for y. So now if I picked an x of 0, I could plug 0 in everywhere there's an x, and it would give me the corresponding point. Or if I plug in 2 for x, I could plug it in both places, both here and here, and it would give me that corresponding point. Because as we saw when we graphed those, we have an infinite number of solutions, and we just need to find those. So if your system of equations gives you a false statement, there is no solution and you've got parallel lines. If your system of equations gives you a true statement, where the variables are both eliminated, then you have a consistent equation and you have two lines, one on top of the other. And you'll have both of those show up in the homework. So there's either no solution because they're parallel, or you have an infinite number of solutions because one is on top of the other. Or you would be able to eliminate one variable and solve for the other, and you would be able to get a single point. Those are the three types of problems we'll see. Now, I do want to bring up one of the word problems so that you can see how we're going to make these solvable. As you can imagine, come up with equations that govern what's going on, and we just need to find the solution to that system. And we will solve it with elimination or substitution, one or the other. So I'm pulling up the textbook so I can copy a problem over. What we're looking at with this particular problem are snack mixtures. And I had a student do something like this for their signature assignment, because you know how you've got that second option that's math is real, where you get to pick your assignment. And actually what they did was something from section 9.7 called linear programming that expands a little bit on this. But let's see what we have here. At Max's Munchies, we've got caramel corn that has a value of $2.50 per pound. It's mixed with honey roasted mixed nuts worth $7.50 per pound. We need to get a 20-pound mixture worth $4.50 per pound. How much of each snack are we going to use? Well, let's create a table. I think that you will find that a figure can be helpful in these problems, but a table is really helpful. So we've got corn, and I know it's caramel corn. I'm just going to use a C. We've got mixed nuts. They've got a dollar value. We've got how many pounds it is. And so let's see what we've got. Caramel corn is $2.50 per pound. We don't know how many pounds, so I'm going to say that's C for caramel corn. We know that the mixed nuts are $7.50 per pound, and we know that we don't know how much we're using, so we'll call that N. Now, if I give you a price per pound, and say we buy 2 pounds of that, you would multiply the price by the number of pounds, right? And so I think we may have to do something like that. Our price per pound times pounds is the total cost. Maybe we don't have to, let's see. So we know we want 20 pounds. And we know we want the mixture to be 4.5 per pound. So C plus N is my 20 pounds. I think we need total cost in here. So dollars per pound times C, so 2.5 C is the total cost. 7.5 times N would be the total cost for the nuts. And So this one, just like we did, 2.5 times C equals that. 7.5 times N equals that. So 4.5 times 20 is, what do we have, 90? 4.5 times 20. So we've got a couple of equations here. This price per pound, you don't just add those together to get the total price per pound. It never works out that way. You actually have to use this one. So let's see what we've got. We've got two equations. We've got C plus N equals 20, and we've got 2.5C plus 7.5N equals 90. So that is our system of equations. You know, those decimals aren't my favorite. I mean, it's not bad, but I deal better with integers. So I'm going to go ahead and take this one and multiply it by 10. And when I do that, I get 25C plus 75N equals 900. Just multiplying each of those by 10. I'm just distributing the 10 through. So I think I'm also going to multiply this one by negative 25. And I'm doing that because that will eliminate the C. So I've got negative 25C minus 25N equals negative 20 times 25 would be 500. And I'm doing that in my head. I do 2 times 25, which is 50, and then times 10. Add the 0 on the end. And now I can just add those two together. 25 plus negative 25 is 0. 75 plus negative 25 is 50. 900 plus negative 500 is 400. I can divide both sides by 50. And N would equal 8. Knowing that, I can now take that 8 and plug it in to any of my other equations, and that one's a pretty easy one to plug into. So I've got C plus 8 equals 20. Subtract 8 from both sides. So I've got that C is 12, so candy corn, we are taking 12 pounds. Mixed nuts, we'll just grab 8 pounds of that. So that's a total of 20 pounds. And if we plug those into this formula, we will find that sure enough, it comes out to be $4.50 per pound. Because 7.5 per pound times 8 plus 2.5 per pound times 12 gives us $90, and divide by the 20 pounds is $4.50 per pound. So it really just wants how much of each snack is used, and this is how we'll do it. We created a table with all of the data. That table gave us our formulas. There was one right there, and there was a second one right there. And then I used elimination. I multiplied both of the equations by something so that one of the variables would be eliminated. I could solve for the other and then plug that one back into one of my initial equations to solve for the first. And that's how we solve these. Do you have any questions? We'll do another one. Because I know these aren't necessarily everybody's favorite. Work on word problems. I like them because it shows the application. That whole question, when am I going to use this? That's what word problems are answering. This is exactly a time when you would use this. Plus, I like to apply the stuff I'm learning. Makes it so I can see value in it. And if I can see value, I'm more likely to remember it. So let's look at this one. An airplane flies 3,000 miles from LA to New York. So just kind of playing around here, we've got US. Not a great picture, but it doesn't matter. I'm going from LA to New York. So that's 3,000 miles between the two. So when it's flying with the wind, it takes 5 hours. I don't know if you know, but the prevailing winds in the United States are from west to east. Tends to be the way it goes because of the rotation of the Earth. So the return trip, when it's fighting the wind, coming back to LA, it took 6 hours. So we've got a difference there. Now when I see that, we've got time, we've got distance, we've got wind, it's asking me for speed. That reminds me of that equation that we learned, that distance equals rate times time. I'm going to take advantage of that idea, and I'm going to go ahead and create a table with distance, rate, and time. So I'm going to go to and back. So when I go to, I go 3,000 miles. I don't know my rate, but I'm flying, and I'm going with the wind when I'm traveling, and it took me 5 hours. When I come back, I also travel 3,000 miles. I've got my plane, but I'm fighting the wind, so the wind is a negative, and it takes me 6 hours. Well, there's my formula. Distance equals rate times time. There we go. My table put it together for me. So I've got 3,000 equals, I'll go ahead and distribute the 5 through here and the 6 through there. So 5p plus 5w. And then we've got 3,000 equals 6p minus 6w. Well, you know what? This would be a lot easier if I divided everything in this first equation by 5 and everything in the second equation by 6. So 3,000 divided by 5 is 600. 5 divided by 5 is 1. 5 divided by 5 is still 1. And then dividing by 6, 3,000 divided by 6 is 500. 6 divided by 6 is 1. And 6 divided by 6 is still 1. So now you can see I have made it so that I can just add these two together and the w's will be eliminated. 600 plus 500 is 1,100. P plus P is 2P. W minus W is 0. Divide by 2, and P equals 550. So that's the speed of my plane. I can plug that P into any one of these. Subtract 550 from both sides, and I've got the wind speed, and I've got the plane speed. Now this is where I remind you that the variables I use match what they stand for. With the previous problem, the variables I used were C for corn and N for nuts. So when I solved it, I knew exactly what the number represented. When I had n equals 8, I knew that was mixed nuts is 8 pounds. When I had C equals 12, I knew that that meant that caramel corn was 12 pounds. With our current problem, I've got P for plane and W for wind, so that when I solved for P, I knew exactly that that was the plane speed. And then I solved for W and knew right away that that was the wind speed. If I use X and Y, which often shows up when people are solving these, I could finish it and, okay, X is 550, but what does that mean? I'd have to go back and figure out what did I call X and hope I didn't make a mistake when I'm going back. If you label your variables with letters that make sense, the odds of you understanding what the result means go up greatly. And so I highly recommend it. Clearly not required, but I think it will save you time and anxiety if you label your variables correctly. But that's another nice equation or problem to show us how to use a system of equations and solve for plane speed and wind speed given the conditions that we had. We did have to remember that equation, that distance equals rate times time. We learned that back when we were talking about linear calculations. But so that's one of those things that's going to keep coming up, especially if you take physics. That'll show up. But a good example of how we can solve these. So that is pretty much what we do in 9.1. Now we've got about 7 minutes. I'm going to go ahead and start 9.2. We may have to finish it tomorrow, but I'd like to at least get it started. Before I do that, are there any questions? Okay. With 9.2, we are extending beyond 2 dimensions. So thus far, well, in 9.1, actually, throughout the class, we have stayed in one plane, one flat surface. We've had X and Y, or real and imaginary. Regardless, we were staying on a flat surface, and now we're adding the third dimension, not just length and width, but also height. And that third dimension gets a third variable. So we are now looking at a system of equations with 3 variables. Say x minus 2y plus 3z equals 11. And 4x plus 2y minus 3z equals 4. And 3x plus 3y minus z equals 4. So we've got 3 variables, and as it turns out, in order to solve a system of equations, you have to have at least the same number of equations as you have variables. You cannot solve a system of equations of 2 equations with 3 variables. It cannot be done. But you can if you've got 3 equations and 3 unknowns. So you've always got to have at least the same number of equations as you have unknowns. But what we're going to do to solve this is use elimination twice to eliminate the exact same variable. And that will give us 2 equations with 2 unknowns, which we can then solve like we did in 9.1, and then come back and figure the missing unknown. So notice that if I add 1 and 2 right now, I've got a 3z and a negative 3z. And those will eliminate z. So let me go ahead and add 1 and 2. X minus 2y plus 3z equals 11. And 4x plus 2y minus 3z equals 4. When I add those together, I get 5x minus, oh, y is gone too. So not minus anything, equals 15. Both of those were eliminated. I didn't notice that at first. I wanted to get rid of z, but both got eliminated. So we can actually right now solve for x. Just divide both sides by 3. So that works out. It's just kind of lucky. Now let's get rid of z with one of our other equations. Let's add 1 plus 3 times equation 3. So what I'm saying is I'm going to take equation 1, and then I'm going to add to that 3 times equation 3. So that would give me 9x plus 9y minus 3z equals 12. So I just multiplied every term in equation 3 by 3. Now when I add these together, I get 10x plus 7y. The z's are canceled, equals 23. So what I have created is an equation 4 and equation 5. But because equation 4 is so simple, I can just plug that into 5. And it will allow me to solve for the other variable. So 4 solves for x. So now into 5, I've got 10 times 3 plus 7y equals 23. I'll go ahead and subtract 30 from both sides. So I get 7y equals negative 7. Divide by 7 and y equals negative 1. I know what y equals, I know what x equals, and now I need to find z, so I can plug both of those. I could do x and y into 1, 2, or 3. Let's go into, oh, I don't know that it matters. Let's go into 1. So we've got x, which is 3, minus 2 times y, which is negative 1, plus 3z equals 11. So let's see, we've got minus a negative here, so that's going to be plus. 3 plus 2 is 5, so if I subtract 5 from both sides, I get 3z equals 6, so z equals 2, dividing both sides by 3. So those are the 3 variables. That means the point of intersection of these 3 lines is x, y, z. That is the solution of this system of equations. We still have the potential for 2 lines to be the same line, but it's much harder now because we're in 3 dimensions. But in all of these problems, we will solve them the same way. We will eliminate one variable using 2 of the equations. And then using the third equation and one of the first ones, we will eliminate the exact same variable. And then we will have 2 equations with 2 unknowns. And I'm saying that because if y had not been eliminated here, we would have had an x term and a y term. Then we would have had 2 equations with 2 unknowns, which we would have solved using either substitution or elimination to get one of the variables, plug that back into equation 4 or 5 to get the second variable, and plug both of those into one of the first equations to get the third variable. And we're out of time, so we'll work more on that tomorrow. I'll solve a couple more problems so that you get a little more used to that. And then we will also do section 9.7 tomorrow, which is using this concept to understand how to get a maximum profit or a minimum cost, not using the parabolic shape like we had before, but looking at intersections of lines. Really cool thing called linear programming. And we'll also look at some inequalities. But before we go, do you have any questions? Okay, that being the case, I hope you have a good day, and I will see you tomorrow. You're welcome.
Thank you. Have a good one.
You too.